Hello there, and welcome to the Sleepy Science Astro. I'm so glad you found your way here because tonight we'll be drifting through distant worlds beyond our solar system. Wherever you are right now, let this be your moment to slow down. Let the noise of the day soften, the edges blur, and your thoughts settle like stardust on a quiet planet's surface. Tonight, we're traveling to exoplanets, worlds orbiting distant stars. Places so far away that their light takes years, decades, even centuries to reach us. From scorching hot Jupiters to frozen super-Earths, from planets with glass rain to worlds orbiting binary stars, the universe holds more variety than we ever imagined. Some of what you hear may surprise you, while other discoveries might simply drift by like clouds on an alien sky, gentle, curious, and quietly unforgettable. If this kind of peaceful wonder brings you calm or sparks your curiosity, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, let yourself get comfortable. Take a deep breath and let's begin this slow and soothing journey through the exoplanets scattered across our galaxy. For thousands of years, humans looked up and wondered if other worlds existed beyond our solar system. But it wasn't until 1995 that astronomers Michel Mayor and Didier Queloz confirmed the first exoplanet orbiting a Sun-like star. They named it 51 Pegasi b, a gas giant orbiting incredibly close to its parent star. This discovery changed everything. It opened the door to a new era of astronomy, proving that planets around other stars were not just theoretical possibilities, but real, detectable worlds. Since then, thousands more have been found, each one adding to our understanding of how diverse planetary systems can be. That first discovery was like lighting a candle in the darkness, and now the sky is filled with the glow of distant worlds. As of now, astronomers have confirmed the existence of over 5,000 exoplanets, and the number keeps growing. These worlds range from scorching gas giants larger than Jupiter to rocky planets smaller than Earth. They orbit stars of all types, at all distances, in configurations we never expected. Some take just hours to complete an orbit, while others take hundreds of years. This vast catalogue represents only a tiny fraction of what's out there. Our galaxy alone may contain hundreds of billions of planets. Each discovery adds another piece to the cosmic puzzle, revealing patterns, oddities, and possibilities. We are still in the early chapters of understanding planetary diversity, and the story is unfolding slowly, gently, one distant world at a time. Among the first exoplanets discovered were the hot Jupiters, massive gas giants that orbit their stars at distances closer than Mercury orbits our Sun. These planets complete their orbits in just a few days, sometimes even hours. Their proximity to their stars means they're scorched by intense radiation, with surface temperatures reaching thousands of degrees. Despite their size, they move swiftly, locked in tight gravitational embraces with their host stars. Scientists initially thought such planets couldn't exist because gas giants were expected to form far from their stars where it's cold. But hot Jupiters likely migrated inward over time, drifting through their solar systems in slow cosmic wanderings. They remind us that planetary systems are dynamic, ever-changing, and full of movement we're only beginning to understand. Imagine a world where oceans stretch not just across the surface, but deep into the interior. Some exoplanets may be water worlds, planets covered entirely by liquid or ice with no exposed land. These planets could have oceans hundreds of kilometers deep, far deeper than anything on Earth. Beneath the surface, the pressure would be immense, potentially creating exotic forms of ice that remain solid even at high temperatures. Some water worlds might have steamy atmospheres thick with vapor, while others could be frozen solid, their surfaces glistening like cosmic snowballs. These planets challenge our definitions of habitability. Water is essential for life as we know it, but too much water, with no land or minerals cycling through the system, might make life less likely. Still, The idea of an endless ocean world drifting silently through space holds a certain serene beauty. One of the most successful ways to detect exoplanets is by watching stars very carefully. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the star's light. This causes a small, brief dip in brightness, a dimming so subtle it requires sensitive instruments to detect. By measuring these dips repeatedly, astronomers can confirm the presence of a planet, estimate its size, and determine how long it takes to orbit. This technique, called the transit method, has been used by missions like Kepler and TESS to discover thousands of exoplanets. It's a quite patient process. Astronomers watch the stars, waiting for the telltale flicker, the shadow of a distant world crossing the light of its sun. In that flicker lies proof of another place, another orbit, another chapter in the cosmic story. In a sky lit by two suns, a planet can trace a path around both, caught in the gravitational embrace of a binary star system. These circumbinary planets, sometimes called Tatooine-like worlds, after the famous fictional desert planet, have been found orbiting pairs of stars that dance around each other. The planet's orbit must be stable enough to avoid being flung away or pulled into one of the stars, a delicate balance maintained over millions of years. On such a world, sunsets would be extraordinary. Two suns sinking below the horizon, casting double shadows, bathing the landscape in overlapping hues of light. The existence of these planets shows that even in complex, chaotic systems, planets can find their rhythm. They adapt, they endure, and they orbit in quiet harmony between two glowing hearts. Not all planets remain bound to their stars. Some, through gravitational interactions with other planets or stars, are flung out into interstellar space, becoming rogue planets. These wanderers drift alone through the galaxy, no longer warmed by a sun, no longer held in orbit. They travel in darkness, cold and solitary, moving between the stars. Despite their isolation, rogue planets may still retain internal heat from their formation or from radioactive decay in their cores. Some might even have atmospheres thick enough to trap warmth, creating pockets of liquid water beneath icy shells. These orphaned worlds challenge our understanding of what a planet is. Without a star, they are invisible, detectable only through rare gravitational effects or infrared glow. They are the silent wanderers of the cosmos, drifting endlessly through the void. Super-Earths are a common type of exoplanet, yet they have no equivalent in our own solar system. They are rocky planets with masses between 1.5 and 10 times that of Earth, larger and more massive but not quite gas giants. Some super-Earths might be scaled-up versions of our world with thicker atmospheres, stronger gravity, and more intense geological activity. Others could be entirely different, with surfaces of molten lava, thick clouds of steam, or frozen wastelands. Scientists aren't sure how these planets form or what their interiors look like. Their existence suggests that planetary formation is more flexible than we thought, capable of producing worlds in a wide range of sizes and compositions. Super-Earths fill a gap in the planetary spectrum, bridging the divide between the small rocky worlds and the giant gas planets. On the hottest exoplanets, temperatures soar so high that metals can evaporate into the atmosphere. Iron, magnesium, and other elements vaporize and condense into clouds, creating skies unlike anything we see on Earth. These metallic clouds might form rain, droplets of molten iron falling through the atmosphere, glowing as they descend. The atmospheres of such planets are dynamic and extreme, with winds that can reach thousands of kilometers per hour, carrying metallic vapor across scorching daysides and freezing nightsides. Observing these planets requires looking at the light filtering through their atmospheres during transits, revealing the chemical fingerprints of exotic materials. These worlds are laboratories for extreme physics, showing what happens when temperatures push matter into strange, beautiful, and violent states. stars don't sit perfectly still. When a planet orbits a star, its gravity tugs on the star, causing it to wobble slightly. This wobble is tiny, but it can be detected by measuring the star's light. As the star moves toward us, its light shifts slightly bluer. As it moves away, the light shifts redder. This Doppler shift, the same effect that changes the pitch of a passing siren, reveals the presence of an unseen companion. The radial velocity method, as it's called, was one of the first techniques used to find exoplanets and remains a powerful tool today. By studying the rhythm of a star's wobble, astronomers can infer the mass and orbit of the planet pulling on it. It's a gravitational dance, subtle and silent, played out across light years, detected by the gentle shifts in starlight. Even after a star dies, planets can remain. Pulsars, the rapidly spinning remnants of massive stars that exploded as supernovae, sometimes host planets. These pulsar planets orbit in harsh environments, bathed in intense radiation and magnetic fields. The pulsars emit beams of radio waves that sweep across space like cosmic lighthouses, and tiny variations in the timing of these pulses can reveal the presence of orbiting planets. It's thought that these planets either survived the supernova explosion or formed afterward from the debris. Either way, they are silent witnesses to stellar death, worlds that endure in the aftermath of catastrophe. Orbiting a pulsar, these planets experience conditions unlike anywhere else. A fitting reminder that planets can exist in even the most extreme corners of the universe. On some exoplanets, the weather is far stranger than anything we experience on Earth. One such world, HD 189733b, is a hot Jupiter with winds reaching over 8,000 kilometers per hour. The extreme heat causes silicate particles to vaporize and condense into tiny, glass-like shards. These particles are then whipped across the planet by ferocious winds, creating horizontal rain made of glass. The atmosphere glows a deep blue, not from water, but from the scattering of light by silicate particles. It's a beautiful, violent world where storms rage endlessly and the air itself cuts like knives. Observing such planets helps scientists understand atmospheric dynamics under extreme conditions, expanding our knowledge of how weather works across the cosmos. In these alien skies, beauty and danger swirl together in an endless, glittering tempest. Mini Neptunes are planets smaller than Neptune, but larger than Earth, typically with thick hydrogen and helium atmospheres surrounding rocky or icy cores. They are incredibly common in the galaxy, yet we have nothing like them in our solar system. This makes them both familiar and mysterious. Scientists don't fully understand how mini Neptunes form or what their interiors are like. Some might be water-rich worlds with deep oceans beneath thick atmospheres. Others could be more like scaled-down gas giants with no solid surface at all. Their prevalence suggests that the conditions that create them are widespread, making mini Neptunes a key piece in understanding planetary formation across the galaxy. They are the quiet majority, filling the space between the extremes. Common yet enigmatic, many exoplanets, especially those orbiting close to their stars, are tidally locked, meaning one side always faces the star while the other remains in permanent darkness. This creates extreme temperature differences. The day side can be scorching hot, while the night side is frozen. On such worlds, there may be a narrow band along the terminator, the boundary between day and night, where temperatures are moderate enough for liquid water to exist. This twilight zone could be the most habitable region, a strip of perpetual sunset or sunrise. The skies would never change. On the day side, the sun would hang motionless in the sky. On the night side, eternal darkness. These planets challenge our ideas of habitability, showing that life, if it exists, might thrive in the strangest, most liminal spaces. Among the thousands of exoplanets discovered, one stands out for its similarity to Earth. Kepler 452b orbits a sun-like star at a distance that places it squarely in the habitable zone, the region where liquid water could exist on the surface. It's about 60% larger than Earth and takes 385 days to complete an orbit, similar to our own year. Its star is slightly older and brighter than our Sun, suggesting that Kepler 452b has had ample time for complex chemistry and perhaps even life to develop. We don't yet know if it has an atmosphere, oceans, or land, but its potential has captured imaginations. It's a reminder that somewhere out there, under a distant sun, a world might be spinning through space with conditions not so different from our own. A cousin in the cosmic family, separated by 1/400 light-years. Red dwarf stars, small, cool, and long-lived, are the most abundant type of star in the galaxy, and many of them host planets. These planets often orbit very close to their dim stars to receive enough warmth, completing their orbits in just days or weeks. Because red dwarfs are so common and long-lived, potentially burning for trillions of years, the planets around them have vast amounts of time for evolution and change. However, red dwarfs can be volatile, emitting powerful flares that could strip away planetary atmospheres. Despite these challenges, some scientists believe red dwarf planets could be habitable, especially if they have thick atmospheres or magnetic fields to protect them. With so many red dwarfs in the galaxy, their planets represent some of the most numerous and enduring worlds in existence. In 2017, astronomers announced the discovery of the TRAPPIST-1 system, a red dwarf star orbited by 7 Earth-sized planets. 3 of these planets lie in the habitable zone, where temperatures might allow liquid water to exist. The planets are packed close together, orbiting in a tight, resonant pattern that keeps them stable. On one of these worlds, you could look up and see the neighboring planets looming large in the sky, some appearing bigger than our moon. The system is about 40 light-years away, relatively close in cosmic terms. TRAPPIST-1 has become one of the most studied exoplanet systems, a target for telescopes seeking signs of atmospheres, water, or even life. It's a reminder that entire planetary families can exist around the smallest stars, quiet neighborhoods in the vast expanse of space. Planets with extreme orbital configurations can experience permanent day or night, depending on their position and tilt. Tidally locked planets, as mentioned, have hemispheres of eternal light and dark. But even planets with slight axial tilts, if they orbit very close to their stars, might have polar regions bathed in endless sunlight or shadow, similar to Earth's polar day and night, but far more extreme. On such worlds, the concept of a day as we know it doesn't exist. Time would be measured differently, perhaps by the passing of orbital cycles or the slow drift of stars in the sky. These planets challenge our understanding of time, rhythm, and the cycles that govern life. In a place where the sun never sets or never rises, existence would unfold in a single, unchanging luminance or darkness. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Dozens of exoplanets have been found in habitable zones around their stars, ranging from red dwarfs to sun-like stars. Being in the habitable zone doesn't guarantee life, of course. A planet also needs the right atmosphere, magnetic field, and geological activity, but it's a promising start. These planets are priority targets for study, especially as new telescopes come online with the ability to analyze their atmospheres for biosignatures, chemical signs that life might be present. Each habitable zone planet is a question mark, a possibility, a world where conditions might, just might, allow for the chemistry of life. The universe is nearly 14 billion years old, and planets began forming not long after the first stars ignited. Some exoplanets are ancient, formed when the universe was just a few billion years old. These planets have existed for 10 billion years or more, far longer than Earth's 4.5 billion years. If life arose on such worlds, it would have had an enormous amount of time to evolve and develop. Civilizations, if they existed, could be billions of years more advanced than humanity. These ancient planets orbit old stars, some of which are nearing the end of their lives. The planets have witnessed cosmic history unfold, seen generations of stars live and die, and drifted through eras we can barely imagine. They are the elders of the galaxy, silent and patient, carrying secrets from the deep past. In some planetary systems, the chemistry is tilted toward carbon rather than oxygen. In such environments, planets can form with compositions vastly different from Earth's. Instead of silicate rocks, these worlds might have surfaces and mantles made of graphite or diamond. Deep within, immense pressures could compress carbon into crystalline structures, creating layers of diamond kilometers thick. These carbon planets would be dark, dense, and alien, with geology unlike anything we know. Rain might fall as tar, and the skies could be thick with sooty clouds. Scientists have identified a few candidate carbon planets, though confirming their composition is difficult. They represent another branch in the tree of planetary diversity, showing that the building blocks of worlds can be arranged in countless, surprising ways. By studying exoplanets, scientists gain insight into the processes that shaped our own solar system. Observing how planets form around young stars, how they migrate through their systems, and how they interact with each other provides clues about Earth's history. For example, the discovery of hot Jupiters showed that giant planets can move inward over time, which may explain irregularities in our solar system's structure. Exoplanets also revealed the diversity of outcomes from planetary formation, showing that our solar system is just one possibility among many. Each new discovery refines our models, helping us understand the forces, timings, and materials that led to the creation of the planets we call home. In the distant stars, we see reflections of our own origins. Most exoplanets have been found around isolated stars, but planets also exist in star clusters, regions where hundreds or thousands of stars are packed closely together. In such environments, planets experience gravitational interactions not just from their own star, but from neighboring stars passing nearby. These encounters could destabilize orbits or even strip planets away from their host stars. Despite these challenges, planets have been found in clusters, showing that they can form and survive even in crowded dynamic regions. The night skies on such planets would be breathtaking, filled with bright stars, some close enough to cast shadows. Living in a star cluster would mean being part of a dense cosmic neighborhood, where the universe feels closer, brighter, and more connected. With the launch of the James Webb Space Telescope, a new era of exoplanet exploration has begun. Webb's powerful infrared instruments can analyze the atmospheres of exoplanets by studying the light that passes through them during transits. This reveals the chemical composition, temperature, and even weather patterns of distant worlds. Scientists are searching for molecules like water vapor, methane, carbon dioxide, and oxygen, which could indicate habitability or even life. Early observations have already revealed surprising atmospheric features, including clouds, hazes, and unexpected chemical compositions. Webb is giving us the ability to move beyond simply finding exoplanets to truly understanding them, peering into their skies and unraveling the mysteries of their climates and chemistries. Some exoplanets orbit so close to their stars that their surfaces are perpetually molten. These lava planets are tidally locked, with daysides hot enough to vaporize rock. Oceans of molten lava cover their surfaces, glowing red and orange, churning under intense heat. The night sides, though still scorching, might cool enough for the lava to solidify into a thin crust, only to melt again as the planet's rotation or geological activity brings it back toward the heat. Some lava planets may have atmospheres of vaporized rock, silicate clouds that rain molten droplets back onto the surface. These extreme worlds show the power of stellar radiation and gravity to shape planets into forms almost unimaginable. They are furnaces in space, glowing embers orbiting their stars. Exoplanets have been discovered around a stunning variety of stars, from tiny red dwarfs to massive, hot blue giants. They orbit old, dying stars and young, newly formed ones. Some planets even orbit the remnants of stars like white dwarfs and pulsars. This diversity shows that planet formation is a robust process, capable of occurring under a wide range of conditions. The size, temperature, and age of a star influence the types of planets that form, but planets themselves are adaptable, finding ways to exist in nearly every stellar environment. This universality suggests that planets are a fundamental feature of the galaxy, woven into the fabric of cosmic evolution. Wherever stars shine, planets are likely nearby. Most planets reflect some of the light from their stars, but a few exoplanets are so dark they reflect almost nothing. One such planet, Tari S2b, reflects less than 1% of the light that hits it, making it darker than coal. The extreme darkness is likely due to its scorching atmosphere, which contains light-absorbing chemicals like vaporized sodium and titanium oxide. Despite absorbing so much light, the planet doesn't appear black in the traditional sense. It glows faintly with its own heat, a deep red like a smoldering ember. These ultra-dark planets challenge our assumptions about planetary atmospheres and show that even in the same category, no two exoplanets are quite alike. In the darkness, they remain visible only by the heat they cannot hide. Beyond simple binary systems, some planets orbit in even more complex configurations. In hierarchical systems, a planet might orbit one star, while that star orbits another, creating a multi-layered dance of gravity. Other planets orbit in triple or even quadruple star systems, navigating gravitational fields shaped by multiple massive bodies. These systems require delicate balances to remain stable, and the planets within them experience wildly varying light and heat as different stars rise and set. The dynamics are chaotic but beautiful, governed by mathematical rhythms that play out over millennia. On such a world, the sky would be a constantly shifting canvas, suns of different colors moving in patterns that trace the geometry of gravity. It's a cosmic ballet, silent and enduring. Planets similar in size and composition to Uranus and Neptune, often called ice giants, appear to be quite common in the galaxy. These planets have thick atmospheres of hydrogen and helium surrounding mantles of water, methane, and ammonia ices. Unlike gas giants, which are mostly hydrogen, ice giants have more solid or liquid material in their interiors. Studying exoplanet ice giants helps scientists understand the diversity of planetary compositions and the conditions under which different types of planets form. Some ice giants orbit in the habitable zones of their stars, raising the possibility of moons around them that could support life. These worlds represent a middle ground between rocky planets and gas giants, filling yet another niche in the spectrum of planetary possibilities. While Saturn's rings are the most famous in our solar system, some exoplanets may have ring systems far more massive and extensive. One planet, J1407b, is thought to have rings 200 times larger than Saturn's, so huge they would be visible from Earth if the planet were in our solar system. These rings might contain enough material to form several moons over time. The rings eclipse the planet's star periodically, creating complex patterns of dimming that astronomers can detect from light years away. Such ring systems are dynamic, evolving, and likely temporary on cosmic timescales. They represent moments of beauty in planetary history, fleeting epochs when dust, ice, and gravity align to create something magnificent. In the silence of space, these rings spin, catching starlight in their frozen embrace. Gravitational microlensing is a technique that uses the bending of light by gravity to detect exoplanets. When a star passes in front of a more distant star from our perspective, its gravity acts like a lens, magnifying the background star's light. If the foreground star has a planet, the planet's gravity creates an additional brief spike in brightness. This method can detect planets at great distances, even thousands of light years away, and is sensitive to planets that other methods might miss. Microlensing events are rare and unpredictable, requiring constant monitoring of millions of stars. But when they occur, they reveal planets in distant parts of the galaxy, expanding our map of worlds far beyond the reach of other detection techniques. It's a method born of patience, waiting for the universe to align just right. Free-floating planets, untethered to any star, drift through the galaxy in vast numbers. Some estimates suggest there could be more rogue planets than stars, making them one of the most common types of objects in the Milky Way. These planets were either ejected from their solar systems or formed independently in interstellar space. Without a star to warm them, they are cold and dark, detectable only through infrared radiation or rare gravitational effects. Some rogue planets might retain enough internal heat to support subsurface oceans, creating isolated pockets of potential habitability. They are the nomads of the galaxy, wandering alone through the void, carrying with them the silent possibility that even in darkness, warmth and life might endure. They drift, unseen and uncounted, through the spaces between the light. As telescopes become more sensitive and techniques improve, the rate of exoplanet discoveries continues to accelerate. Missions like TESS, the Transiting Exoplanet Survey satellite, scan the entire sky, identifying thousands of candidate planets. Ground-based observatories equipped with advanced spectrographs detect the tiny wobbles in stars caused by orbiting planets. Future missions, including the European Space Agency's Plato and NASA's upcoming telescopes, will push the search even further, targeting smaller planets and analyzing their atmospheres in greater detail. Each new generation of technology reveals worlds that were previously beyond our reach. The pace of discovery is quickening, and with it, our understanding of the galaxy's planetary population grows richer, deeper, and more surprising. The universe is opening itself to us, one planet at a time. When we search for life on exoplanets, we often look for conditions similar to Earth's: liquid water, moderate temperatures, and certain chemical signatures. But life, if it exists elsewhere, might be radically different. It could be based on different chemistry, thriving in environments we consider extreme. Life might exist in the clouds of gas giants, in subsurface oceans of ice worlds, or even in the atmospheres of planets we've dismissed as inhospitable. The discovery of extremophiles on Earth, organisms that survive in boiling acid, freezing ice, and crushing depths, has expanded our definition of habitability. As we study exoplanets, we must remain open to the possibility that life takes forms we haven't yet imagined. The universe is vast, and its creativity in arranging matter into living systems may be boundless. The naming convention for exoplanets is simple but systematic. They are named after their host star, followed by a lowercase letter indicating the order of discovery. The first planet discovered around a star is designated B, the second C, and so on. The star itself is often named after the survey or catalogue that identified it, like Kepler 4522 or TRAPPIST-1. While these names lack the romance of fictional planets, they serve a practical purpose, organizing the growing catalogue of worlds in a clear, consistent way. Some exoplanets have been given unofficial nicknames like Osiris or Bellerophon, but the scientific names remain the standard. Behind each designation lies a story of discovery, of light measured, data analyzed, and a new world added to humanity's map of the cosmos. While many exoplanets have nearly circular orbits, others follow highly elliptical paths, swinging close to their stars at one point and far away at another. These eccentric orbits cause dramatic variations in temperature and radiation over the course of a single year. A planet on such an orbit might experience scorching summers and freezing winters, seasons far more extreme than anything on Earth. The causes of these elliptical orbits are often gravitational interactions with other planets, close encounters that perturb the system and stretch orbits into elongated shapes. Over time, tidal forces from the star can gradually circularize these orbits. But for planets caught in the early, chaotic stages, life on such a world would be one of extremes, a constant cycle of heat and cold. Before the famous discovery of 51 Pegasi b in 1995, the very first confirmed exoplanets were found orbiting a pulsar in 1992. These planets, detected by measuring tiny variations in the pulsar's radio signals, orbit a dead star in a harsh, radiation-filled environment. The discovery was unexpected. Pulsars are the remnants of supernova explosions, and it was thought that any planets would have been destroyed in the blast. Yet these planets survived or formed afterward, proving that planets can endure even the most violent cosmic events. They don't receive warmth or light from their pulsar, only intense radiation. Life as we know it would be impossible there. But the existence of these worlds showed that planets are more resilient and widespread than anyone had imagined. Planets that orbit very close to their stars can experience such intense radiation that their atmospheres are literally boiled away into space. These evaporating planets leave trails of gas behind them as they orbit, creating comet-like tails of escaping atmosphere. Over time, they may lose their gaseous envelopes entirely, leaving behind only rocky cores. Astronomers have observed these planets in various stages of evaporation, providing insights into planetary evolution and the ultimate fate of close orbiting worlds. The process is slow on human timescales but relentless over millions of years. These planets are in a race against time, their atmospheres streaming away into the void, leaving them smaller, denser, and stripped bare under the unforgiving gaze of their stars. When we imagine habitable planets, we often picture Earth-like worlds with continents and oceans. But statistically, planets covered entirely in water, ocean worlds, may be far more common. These planets would have no land, just global oceans potentially hundreds of kilometers deep. Beneath the water, intense pressure might create exotic forms of ice, even at high temperatures. The lack of exposed rock could make it harder for certain types of life to evolve, but microbial life could thrive in the oceans, powered by hydrothermal vents or chemical energy. Some scientists believe that ocean worlds might be the most common type of habitable planet in the galaxy. If so, the search for life should focus not on worlds that look like Earth, but on those covered entirely by water, silent, deep, and teeming with possibility. Most exoplanets are detected indirectly through their effects on their stars, but a few have been directly imaged, appearing as faint points of light in powerful telescopes. Direct imaging is challenging because planets are dim compared to their stars, typically millions of times fainter. To see them, astronomers use coronagraphs or star shades to block the star's light, revealing the planets orbiting nearby. The planets that have been imaged tend to be young, large, and far from their stars, still glowing with heat from their formation. These images are more than just pictures. They are proof that these distant worlds exist, that they orbit and shine in their own quiet way. Each image is a triumph of technology and patience, a glimpse across light years into another solar system. Planets don't always stay where they form. Gravitational interactions with other planets, the protoplanetary disk, or passing stars can cause them to migrate inward or outward over millions of years. Hot Jupiters likely formed farther from their stars and drifted inward, settling into tight orbits. Some planets may migrate outward, pushed by interactions with other massive bodies. This migration reshapes solar systems, causing collisions, ejections, and dramatic changes in planetary climates. Understanding migration helps explain the diversity of exoplanet systems and the sometimes chaotic arrangements we observe. Planets are not fixed in place but are part of a dynamic, evolving system. They move through space like dancers in a slow gravitational ballet, their paths shaped by forces seen and unseen. Some exoplanets orbit their stars so closely that they complete a full orbit in mere hours. These ultra-short period planets are typically small, rocky worlds, stripped of their atmospheres by intense radiation. They race around their stars at incredible speeds, locked in tight gravitational grips. On such a world, the sun would rise and set multiple times in what we'd consider a single day. The surface would be scorched on the day side and possibly cooler on the night side, though the rapid rotation might even out temperatures somewhat. These planets challenge our understanding of orbital mechanics and planetary survival. They are extremes made real, worlds that push the boundaries of what's possible in the delicate dance between gravity and motion. Despite thousands of discoveries, exoplanet science is still a young field. The first confirmed exoplanet around a Sun-like star was found less than 30 years ago. We've barely begun to explore the diversity of worlds in our galaxy, and new surprises emerge with every mission. Future telescopes will allow us to study exoplanet atmospheres in unprecedented detail, search for biosignatures, and perhaps even image Earth-sized planets in habitable zones. The next few decades will likely bring discoveries that reshape our understanding of planets, life, and our place in the universe. We are explorers at the dawn of a new age, mapping a cosmic landscape that stretches beyond imagination. Each discovery is a step into the unknown, and the journey has only just begun. The universe is vast, patient, and full of worlds waiting to be found. Most stars and their planets reside in the galactic disk, the flat, spiral-armed region where our Sun orbits. But some planets have been found around stars in the galactic halo, the spherical region of old stars surrounding the Milky Way. These halo stars are often metal-poor, formed early in the galaxy's history when heavier elements were scarce. The discovery of planets around them suggests that planet formation can occur even with minimal heavy elements, contradicting earlier theories that metals were essential for planetary building. These ancient planets drift in the galactic outskirts, far from the bustle of the spiral arms, orbiting old, dim stars in the quiet reaches of space. They are relics from an earlier epoch, witnesses to billions of years of cosmic evolution. Every exoplanet discovery refines our ability to estimate the prevalence of life in the universe. By understanding how many planets exist, how many are in habitable zones, and what conditions they possess, scientists can make educated guesses about the likelihood of life arising elsewhere. The Drake equation, a formula for estimating the number of active communicative civilizations in the galaxy, relies heavily on exoplanet data. While we still don't know how common life is, the sheer number of planets, especially those in habitable zones, suggests that the universe offers countless opportunities for biology to emerge. Whether life is rare or abundant remains unknown. But exoplanets show us that the stage is set, the ingredients are present, and the possibilities are endless. Most planets orbit their stars in the same direction the star rotates, a natural outcome of forming from a spinning disk of material. But some exoplanets have retrograde orbits, moving in the opposite direction. This unusual configuration likely results from gravitational interactions with other planets, which can flip or reverse a planet's orbit over time. Retrograde planets challenge our models of solar system formation and evolution, showing that planetary systems can be reshaped dramatically by internal dynamics. On such a world, the stars would appear to move differently across the sky, and the planet's history would be one of upheaval and change. These backward-orbiting worlds are reminders that the cosmos is not always orderly, that chaos and chance play roles in shaping the systems we observe. Around young stars, disks of dust and gas swirl the leftover material from star formation. Within these disks, planets are actively forming, coalescing from the debris over millions of years. Astronomers have imaged these protoplanetary disks and found gaps, rings and spiral patterns, evidence of planets carving out their orbits as they grow. Observing these systems gives us a window into the planet formation process, showing how worlds are born from cosmic dust. Some of these young planets are still accreting material, growing larger with each passing millennium. They are worlds in their infancy, raw and unfinished, surrounded by the swirling remnants of creation. Watching them form is like witnessing the first breaths of new worlds coming to life. While most exoplanet discoveries occur within our own Milky Way, a few candidates have been identified in other galaxies. These detections are made using microlensing or by observing X-ray emissions from material falling into black holes, with planetary-sized objects causing subtle variations. Confirming these planets is extremely difficult due to the vast distances involved, millions or even billions of light years. But if verified, They would prove that planets exist not just throughout our galaxy, but throughout the universe. These distant worlds orbit stars in galaxies we can barely resolve, places so far away that their light has traveled across cosmic time to reach us. They are the ultimate frontier, planets beyond our galactic borders, silent and unreachable, drifting in the depths of space. Just as Jupiter and Saturn have dozens of moons, some exoplanets likely host their own systems of natural satellites. Large gas giants in particular could have moons of various sizes, some potentially habitable if they orbit in the right zone. These exomoons, as they're called, are difficult to detect because they're much smaller than planets and produce even subtler signals. But astronomers are developing techniques to find them, and a few candidates have already been identified. A moon orbiting an exoplanet in a habitable zone could have liquid water, tidal heating, and a stable climate, making it a prime target in the search for life. These moons would be worlds within worlds, satellites circling planets that circle distant stars, nested layers of orbits in the cosmic dance. Ultra-cool dwarfs are the smallest, coolest stars, barely massive enough to sustain fusion. Despite their dimness, they can host planets, and because the stars are so cool, planets can orbit very close and still remain in the habitable zone. The TRAPPIST-1 system, with its 7 Earth-sized planets, orbits an ultra-cool dwarf. These stars are incredibly common and long-lived, burning for trillions of years, far longer than the current age of the universe. This means planets around them have vast amounts of time for evolution and change. However, ultra-cool dwarfs can be volatile, producing flares that might strip away atmospheres. Despite the challenges, their abundance and longevity make them prime targets in the search for habitable worlds. A few exoplanets, nicknamed superpuffs or cotton candy planets, have extraordinarily low densities. These gas giants are as large as Jupiter, but with only a fraction of the mass, giving them densities comparable to cotton candy or styrofoam. Scientists aren't entirely sure how these planets maintain such low densities. They may have extended atmospheres of hydrogen and helium that are puffed up by internal heat or stellar radiation. These worlds are fragile and ephemeral, likely to lose their atmospheres over time. They challenge our understanding of planetary structure and show that planets can exist in states we never anticipated. Light, airy, and almost insubstantial, they float through space like cosmic ghosts. By analyzing the light that filters through an exoplanet's atmosphere during a transit, scientists can detect clouds, hazes, and weather patterns. Some planets have clear skies, while others are shrouded in thick clouds that obscure their surfaces. Wind patterns, temperature gradients, and atmospheric circulation can all be inferred from spectroscopic data. On some worlds, scientists have detected high-altitude clouds of silicates or other materials, while others show evidence of powerful jet streams and global circulation. Understanding exoplanet weather helps us grasp the physics of atmospheres under diverse conditions, from the mild to the extreme. Each atmosphere is unique, shaped by the planet's size, composition, distance from its star, and countless other factors. Auroras on Earth are caused by charged particles from the Sun interacting with our magnetic field and atmosphere. On exoplanets, especially those with strong magnetic fields and close stellar companions, auroras could be far more intense and frequent. Gas giants with powerful magnetic fields and high levels of stellar radiation might have permanent planet-wide auroras glowing in their upper atmospheres. On tidally locked planets, auroras might concentrate in specific regions, creating glowing caps or rings. These light shows would be invisible to the naked eye from Earth, but future telescopes might detect them through their characteristic emissions. Auroras are not just beautiful, they're windows into a planet's magnetic environment, revealing the invisible forces that shape and protect it. On a planet orbiting 2 stars, the seasons would be far more complicated than Earth's simple cycle. Depending on the planet's orbit and axial tilt, it might experience periods where both stars are in the sky, followed by times when only one is visible. The distance to each star changes over time, creating overlapping seasonal patterns. Temperatures could fluctuate wildly, and the amount of daylight might vary in unexpected ways. Despite this complexity, computer models show that stable climates are possible in circumbinary systems. Life on such a world would adapt to the irregular rhythms of light and heat, evolving under skies lit by twin suns. It's a reminder that habitability doesn't require Earth-like simplicity, only stability and time. Astronomers have identified planets in various stages of migration, slowly spiraling inward toward their stars. These planets will eventually become hot Jupiters, but they're currently in transition, orbiting at intermediate distances. Studying these migrating planets helps scientists understand the mechanisms driving planetary motion, whether through interactions with the protoplanetary disk, gravitational scattering, or tidal forces. Over millions of years, these planets will settle into close orbits, their atmospheres heated and transformed by stellar radiation. They're snapshots of a process that unfolds over vast timescales, offering glimpses into the dynamic evolution of planetary systems. Watching them migrate is like watching time-lapse photography of the cosmos. Just as Uranus in our solar system is tilted on its side, some exoplanets have extreme axial tilts that create bizarre seasonal patterns. A planet tilted more than 90 degrees would have its poles pointing nearly at its star at certain times of year, while its equator would receive little direct sunlight. The seasons would be extreme, with polar regions alternating between eternal day and eternal night over the course of a year. Such tilts likely result from violent collisions or gravitational interactions early in the planet's history. These worlds are testaments to the chaotic origins of planetary systems, where impacts and near misses can permanently alter a world's orientation and climate. In addition to the traditional habitable zone around a star, some planets might have internal habitable zones. Large moons orbiting gas giants could be heated by tidal forces, creating subsurface oceans even if they orbit far from their star. Similarly, planets with thick atmospheres and active geology might maintain surface warmth through greenhouse effects or internal heat, extending the habitable zone outward. Rogue planets with subsurface oceans heated by radioactive decay represent another type of habitability, one that doesn't depend on stellar light at all. The concept of habitability is expanding beyond simple temperature ranges, encompassing a variety of energy sources and planetary configurations. Life, if it's adaptable, might find footholds in places we're only beginning to consider. The first confirmed exoplanets, like 51 Pegasi b, have now been observed for nearly 30 years. This long baseline of data allows astronomers to study changes over time, refining measurements of orbital parameters, detecting additional planets in the system, and observing atmospheric variations. Long-term monitoring reveals patterns invisible in short observations, such as orbital precession, planetary transits of multiple bodies, or slow changes in stellar activity. These veteran exoplanets have become touchstones in the field, referenced in countless papers and used to test new theories. They've watched from afar as humanity's understanding of planets has grown, silent participants in our journey of discovery. White dwarfs are the cooling remnants of sun-like stars, and while they're much dimmer than their progenitor stars, planets can still orbit them. In some cases, planets survive the star's red giant phase or form afterward from debris. The habitable zone around a white dwarf is very close, requiring planets to orbit in tight circles to receive enough warmth. Despite the challenges, these systems offer potential homes for life, especially if planets have water and stable climates. White dwarfs cool slowly over billions of years, providing steady, if dim, illumination. Life around a white dwarf would exist under a faint, reddish light, on a world huddled close to the embers of a once brilliant star. Magnetic fields protect planets from stellar radiation, and solar wind, preventing atmospheric erosion. Earth's magnetic field is generated by its liquid iron core, and some exoplanets likely have similar or even stronger fields. Large, rocky planets, especially those with rapid rotations and active interiors, might generate powerful magnetic fields that extend far into space. These fields could create massive magnetospheres, trapping charged particles and producing intense auroras. Detecting exoplanet magnetic fields is challenging, but astronomers are developing techniques to measure them indirectly through radio emissions or interactions with stellar wind. A strong magnetic field could be essential for habitability, making it a key factor in assessing whether a planet can support life. Globular clusters are ancient, densely packed groups of stars orbiting the outskirts of galaxies. These clusters contain some of the oldest stars in the universe, formed when the galaxy was young. A few planets have been found in globular clusters, though their formation is somewhat mysterious given the low abundance of heavy elements in these old stars. The night sky on such a planet would be extraordinary, with thousands of stars visible, some close enough to cast light rivaling the full moon. However, gravitational interactions in the crowded cluster could destabilize planetary orbits over time, making long-term stability uncertain. These planets are cosmic oddities, worlds formed in the galaxy's youth, drifting through time in ancient stellar cities. Planets orbiting very close to their stars or massive companions experience intense tidal forces, similar to how the moon creates tides on Earth, but far stronger. These forces can stretch and squeeze a planet, generating internal heat through friction. This tidal heating can melt interiors, drive volcanic activity, and even maintain subsurface oceans on otherwise frozen worlds. Io, a moon of Jupiter in our solar system, is the most volcanically active body we know, powered entirely by tidal heating. Some exoplanets likely experience similar or even more extreme tidal effects, with surfaces constantly reshaped by gravitational stress. These forces can make planets geologically active and dynamic, though they can also lead to instability and eventual destruction. The diversity of exoplanets has forced astronomers to reconsider what qualifies as a planet. Is it simply a body orbiting a star? What about rogue planets with no star? Do mass limits apply? The International Astronomical Union's definition, created primarily with our solar system in mind, doesn't always fit the exoplanetary zoo. Brown dwarfs, objects between planets and stars, blur the boundaries further. Some planets are more massive than the smallest stars, while some stars barely sustain fusion. These definitional challenges reflect the complexity of the universe. Categories we create are human constructs, and nature rarely respects our neat classifications. The cosmos is messier, stranger, and more interconnected than our labels suggest. Debris disks are belts of rocky and icy material orbiting stars, similar to our asteroid and Kuiper belts. Some exoplanetary systems have debris disks thousands of times more massive than ours, filled with comets, asteroids, and dust. These disks can indicate ongoing planet formation or the aftermath of violent collisions between planetary bodies. They also pose hazards for any planets in the system, as impacts would be far more frequent. However, such disks might also deliver water and organic materials to planets, potentially seeding them with the ingredients for life. These systems are dynamic and chaotic, with matter constantly colliding, breaking apart, and occasionally coalescing into new structures. They're laboratories for understanding planetary evolution. While Earth takes 24 hours to rotate, some exoplanets spin far more rapidly. Gas giants, especially young ones, can rotate in just a few hours, creating extreme centrifugal forces that flatten them into oblate shapes. Rapid rotation affects atmospheric circulation, creating powerful jet streams and complex weather patterns. On rocky planets, fast rotation might influence magnetic field generation and geological activity. In extreme cases, rotation could even affect the planet's stability, though gravity generally keeps things in check. These spinning worlds are blurs of motion, their surfaces and atmospheres constantly churning, driven by rotational energy that shapes everything from wind patterns to the length of their days. Amateur astronomers and citizen scientists have played crucial roles in exoplanet discoveries. Projects like Planet Hunters allow volunteers to analyze data from space telescopes, searching for the subtle dips in starlight that indicate transiting planets. Several exoplanets have been discovered this way, including some that automated algorithms missed. This collaboration between professionals and enthusiasts democratizes science, allowing anyone with internet access to contribute to cosmic exploration. It's a reminder that discovery isn't limited to those with degrees or access to telescopes. Sometimes all it takes is a careful eye, patience, and the willingness to look closely at data that might hold hidden worlds. Some exoplanets rotate so slowly that their day, the time it takes to spin once on their axis, exceeds their year, the time to orbit their star. Venus in our solar system is one example, and several exoplanets share this characteristic. On such worlds, the Sun would move incredibly slowly across the sky, taking weeks or months to cross from horizon to horizon. This can create unusual temperature distributions and atmospheric patterns. In some cases, these slow rotations are due to tidal locking or near locking, where the star's gravity has slowed the planet's spin over time. These worlds experience time differently, their rhythms stretched and slowed, moving through space at their own unhurried pace. While official designations follow systematic rules, some exoplanets have been given informal names that honor the people or instruments that found them. Others have received names through public contests chosen by vote from submitted suggestions. These names often reflect cultural or mythological themes connecting distant worlds to human stories and traditions. Though the scientific community primarily uses systematic names, these alternative names help personalize the cosmos, making distant planets feel less abstract and more connected to our shared human experience. Each named world carries a story, not just of its own formation and evolution, but of the moment humans first detected its existence and decided to call it by name. Plate tectonics, the movement of crustal plates over a planet's surface, is a key factor in Earth's habitability, recycling carbon, and regulating climate. While we can't directly observe tectonics on exoplanets, scientists believe some rocky planets likely have similar processes. Larger rocky planets, sometimes called super-Earths, might have even more vigorous tectonic activity due to their greater internal heat and gravitational pressure. Tectonics requires a planet to have a molten interior, a solid crust, and the right balance of temperature and composition. Detecting tectonic activity on exoplanets remains a challenge, but future observations of volcanic activity or surface changes might provide indirect evidence. Planets with tectonics would be dynamic, constantly renewing their surfaces and atmospheres. In dense, star-forming regions or during close stellar encounters, planets can be gravitationally captured from one system and pulled into orbit around another star. These captured planets would have chemical compositions and characteristics different from planets that formed in place, offering clues to their origins. They might orbit at unusual angles or distances or have retrograde orbits. Detecting such planets requires careful analysis of their properties and orbits. These cosmic refugees are rare but fascinating, worlds that have experienced two stellar homes, first formed around one star, then stolen away to orbit another. They're travelers between stars, carrying memories of their birthplaces into new systems. Many exoplanets orbit stars similar to our Sun, which will eventually exhaust their hydrogen fuel and expand into red giants. When this happens, the inner planets will be engulfed and destroyed, while outer planets might be pushed outward or have their atmospheres stripped away. Scientists study these systems to understand what will happen to Earth when our Sun enters its red giant phase billions of years from now. Some planets currently in habitable zones will be incinerated, while others, farther out, might warm into habitability temporarily. These systems offer glimpses into the future, showing the inevitable end awaiting planets around Sun-like stars. a reminder that even planets have lifespans. In some exoplanetary systems, planets are locked in orbital resonances where their orbital periods are related by simple ratios. For example, one planet might orbit twice for every single orbit of another, creating a 2.1 resonance. These resonances are stable configurations that can last for billions of years, shaped by gravitational interactions over time. The TRAPPIST-1 system is a striking example, with multiple planets in a resonant chain. Resonances prevent planets from colliding or destabilizing each other, acting like cosmic gears that mesh together smoothly. They're evidence of order emerging from chaos, mathematical harmony, written into the motion of worlds. Carbon monoxide, poisonous to humans, has been detected in the atmospheres of several exoplanets. Its presence reveals information about the planet's temperature, chemistry, and atmospheric circulation. On hot planets, carbon monoxide forms when carbon dioxide breaks apart under intense heat. Its detection helps scientists understand the chemical processes occurring in alien atmospheres and refine models of atmospheric composition. While carbon monoxide makes a planet uninhabitable for humans, it's simply one molecule among many in the vast chemical diversity of exoplanet atmospheres. Each detection adds detail to our understanding, building a chemical portrait of worlds light years away. Proxima Centauri, the nearest star to our solar system at just over 4 light years away, has at least 2 confirmed planets. One of them, Proxima Centauri b, orbits in the habitable zone, though the star's frequent flares might make surface conditions harsh. Other nearby stars like Barnard's star and Lumen 16 also have planets or planetary candidates. These nearby systems are prime targets for detailed study, and someday, perhaps even interstellar probes. If humanity ever travels to another star, these nearest neighbors will likely be our first destinations. They're our closest cosmic companions, systems we could potentially reach in decades or centuries rather than millennia, doorways to the stars that lie tantalizingly within reach. The discovery of thousands of worlds beyond our solar system has captured human imagination, inspiring countless works of science fiction, art, and music. Exoplanets appear in novels, films, and video games, often depicted as settings for future human colonies or alien civilizations. Artists create visualizations of these distant worlds, imagining their skies, landscapes, and atmospheres based on scientific data. The knowledge that real planets exist around other stars has deepened our sense of connection to the cosmos and our place within it. These discoveries remind us that the universe is not empty but filled with worlds, each one a potential stage for stories, life, and wonder. In finding exoplanets, we've found new mirrors for our dreams. We've drifted across light years tonight, visiting worlds of ice and fire, darkness and brilliance. From planets with diamond hearts to those wrapped in endless oceans. We've imagined skies with 2 suns, rain made of glass, and surfaces that never see day or night. Each exoplanet is a reminder of how vast and varied the universe truly is, how many possibilities exist beyond our own small world. You've traveled far without leaving your bed. Your thoughts have crossed the galaxy, touched the atmospheres of alien worlds, and glimpsed the dance of planets around distant stars. And now, as the facts fade into the quiet spaces between thoughts, let yourself sink deeper into rest. The exoplanets will continue their orbits, spinning silently through the cosmos, whether we watch or not. There are still thousands more to discover, millions more waiting to be found. But tonight you've learned enough. You've seen enough. Let the distant worlds fade like stars at dawn, and let your own journey into sleep begin. The universe is patient. It will wait for you to return. Thank you for exploring these distant worlds with me. May your dreams tonight be filled with alien skies, gentle orbit, and the quiet knowledge that somewhere out there, beneath unfamiliar stars, other worlds are spinning through the endless dark. Sleep well and good night.